And our next speaker is Christian Burisch, Director of Global Application Engineering at OneSpin Solutions. The title of the talk is Viewing Formal Through Simulation Tinted Glasses. A good topic, because I often get asked, people often ask me, how do we combine formal and simulation, and how do we use the two together? So I'm always interested in ways of looking at formal from a simulation perspective. Christian is the Director of Application Engineering for OneSpin. After working at Fujitsu, he started his EDA career as an AE and then the first engineer in the Formative Cadence Consulting Group back in the 1990s. He has since held senior AE roles at Ambit, Co-Design, Tennyson, and Methodics, providing him with a varied engineering background. He holds a master's degree in microelectronics. I'll hand over to Christian.
Hi, good morning. So the topic today is to talk a little bit about how simulation and formal can work together and how you can make formal a bit more attractive and workable for simulation users. So, I mean, clearly simulation and formal together are a very powerful combination, but maybe some better connection points are needed to improve the flow. And you know, we've got some things that we've done there in OneSpin and some things that we're planning to do that might be interesting to outline here. So as you all know, the fundamental difference between formal and simulation is, I mean, you've got your design here, you've got loads of transition states that the design can go through, and in simulation you've got one possible path that is driven by a test bench input that it follows, while formal explores the whole design space in parallel. So each of these is useful for different things. So, and simulation is excellent at working out the, it's showing the normal operation of a design. You've got a design that's supposed to do something, you can simulate that and say, like, yep, it does what it's supposed to do. Well, formal is much better at finding, exploring everything and then finding things that can go wrong. So this makes simulation really useful on data path type designs, while formal is really good at debugging things on control paths and data transport. The limitations of that are, of course, that with simulation, because you're only looking at a single state sequence, you can go to an arbitrary clock cycle depth. You can clock the thing for thousands of cycles and to no detriment. Well, of course, with formal, it prefers much shallower clock cycle depths, because the deeper you go, the more state space that you have to explore. So what simulation is really good for is to show that correct behavior happens, and formal is really excellent at finding unanticipated effects. I mean, really corner case bugs that are hiding somewhere that are very difficult to find. And ideally, you want to use both of these things together, because there are some type of corner case bugs that you can imagine that that simulation would have no hope of finding. If you imagine you've got, like the previous speaker was from Gila Logic was talking about some of the bugs that he found in the second examples. You've got something that only happens if you've overflow some FIFO and some counter wraps around at the same time. Well, the design is in a certain mode or something, and then something bad happens. With simulation, it requires you to actually think about that thing, possibly causing a problem, and then driving your test bench there to cause this thing happening, which is major effort. And then that only covers the cases where you've actually thought about it. If something goes wrong, you've got a corner case bug that is completely unanticipated, you're going to miss it. So formal is great for that, just finding things that can go wrong that you never thought about before. So really, clearly, formal and simulation together on verification is what you need. However, they're still pretty disconnected. So in a design team, you might have your formal experts that write complex assertions to verify things. You might have designers and verification guys, writing some assertions in their verification, and you might even have some of the designers themselves running some automated apps on this, and they'll give you value and all this, but it's sort of disconnected from the simulation world. So what you really want is you want to be able to have some combined verification planning, as you can see up there, and you need to have some common coverage models that the formal world uses. You need to connect the debug environment. You want to have consistent stimulus, and it's also quite useful to have formal with a bit of simulation familiarity, because it's a hard thing to get into formal, and you don't want to just have the verification. The formal experts using it. You want to make it useful to more people. So at the verification planning stage, it makes sense to consider formal early in the process. There are all these verification planning tools out there that help you to plan what features you want to test and all this, and it makes sense from there to say, like, there are certain things in your design where you think formal it makes sense to use formal, and you design that up front. You've got some registers in your design. Are the registers actually connected properly according to the IP-exact specification? There might be some key blocks that are extremely important that you might want to verify with formal to a much higher degree than you can with just simulation. You might want to ask certain questions on the design, saying, like, does a certain signal behave exactly the same under all circumstances, and with the right timing, or about certain events that shouldn't happen. Can the certain FIFO actually overflow and show me what needs to happen to make this happen? So these are the things that you could ask at the verification planning stage and then ship out to formal. And then when you run it, you want to be able to interpret the coverage also. So already with formal, you can do pretty cool things about the coverage. When you see in simulation coverage, here's a little example here at the bottom left on that scroll. It says, case state burst, and then if cancel, then something happens. So if you say, show me the simulation coverage, then it says, like, yep, this is covered. It means that state burst actually happened in the simulation while the cancel was high. The cancel signal was high. So this thing's covered. But then, of course, it doesn't say, did the test bench check that the correct behavior was there? So in formal, you can do really cool things built in. For example, here it says this done signals, it's mutated to a question mark there, which means it can be anything. And then you check on the outside, do any of the assertions fail? And if the assertion fails, then it's great. It means you've really covered it by actually checking the observability of a problem. And if it doesn't fail, it means, like, the event can happen, but there is no assertion written to check that this code is actually correct. So this, you can show this graphically here on the right. This is the source code color. You can't read any of it, but no, this is just the source code color coded according to the results of this coverage analysis. So if something is green, it means it's verified. It means this can happen, and if something goes wrong there, an assertion will fail, and you'll pick it up. The red code here in the middle is means that it doesn't. There's no assertion that fails, so it means it gives the verification people some hints on what assertions to write next, because all this requires is extra assertions to make sure that that part of the functionality of the design is actually covered. At the bottom, these last two lines, they're black here. That means it's unreachable code. So it means something that can never happen, and that's something worth looking at. And then there is a quite an interesting thing here. Is the brown code means that's code that is in not operational. It's like the black part, unreachable, but due to constraints. So that's really valuable information to the verification engineers, because it indicates that there's quite probably some over-constraining taking place. You've put some constraints on your design that stop this code ever from being executed. So why has the designer wrote it in the system if it doesn't serve any purpose? So that normally shows there's over-constraining, which can hide bugs. So it's all really quite useful. But then, of course, after you've done this formal coverage, you want to be able to import this into the simulation coverage that you have. So you've got your verification plan. You check that the results that you're getting your coverage from the simulation. You need to be able to port the verification coverage results into there, and there's various different initiatives to make this happen, like the Accelerate UCIS standard. And we're working on that to just make sure that the formal and simulation world can talk to each other and use all these nice verification management and planning tools out there. Another thing that can happen is that's available is if you actually find a bug, you can auto-generate a test from it from formal. So it means you've got a failure. You can see an execution trace. The tool will tell you what the trace is of the inputs to get to the state that triggers the bug. You can look at that on any debugger that you want, but you can also just save it out as a test bench, as the execution trace. So, well, I go back one step. So why would you want this? It's mainly you can hand over the test bench to the designers to rerun. But of course, one big advantage is for regression testing. If finding the failure took you a really long run with formal, and you fix it, you might want to have this test actually in your regression to make sure that it stays fixed, right? Rather than having to rerun the whole formal thing. Of course, what this test bench does is it replaces all your other test bench. It just wiggles the signals according to the certain sequence. So another thing that we're working on right now is to actually backport assertions onto UVM tests. So this is instead of just replacing your test bench, to work with it, so that you can actually auto-generate UVM test bench constraints there from your failure. So that's a work in progress, a project that we're working on right now. And if you're interested in this, it would be nice if you come up later and talk to us about it. Another interesting point is how can you make formal more palatable to simulation users? And one other thing you could do is to use more operational assertions. So that's a particular style of writing an assertion that is much more understandable to simulation people and designers. So it's basically it's not a new language or something. It's just a style of writing your assertion, like here with this imply statement. And basically, an operational assertion is a textual way of describing a waveform. And waveforms are things that all the designers and verification engineers are very, very comfortable with. And it makes it much easier for people who don't have deep training with SVA also to get started with formal and to use it. So that's that's a nice thing. And as a fringe benefit to that is also with the completeness came up at the beginning in your keynote speech. This is if you want to have a block that you want to make absolutely sure that you've got it 100% verified, you can reach 100% coverage by using this thing called completeness, which means that you describe all your assertions as these operational assertions, and you give the tool some more information on how they hang together and what legal sequences of these assertions, and then the tool can tell you whether you've comprehensively and 100% verified your design. And some of the people here listening to the talk at this conference are customers, and they're using this. So basically, a few words on OneSpin. We've got high performance and capacity. We already have this very good quantitative analysis of your coverage with a very precise closure metric. That was the slide that I showed earlier with the different colors on the source code on it. We've got operational assertions, and we're working on integrating the flow to make it with simulation in terms of coverage, and we've got partnerships with Synopsys and Mentor already to push this forward. So finally, just a sort of a general slide. If you're not familiar with OneSpin, what the company is focused on basically are these 6 solution areas there. We're focusing on metric-driven verification, block integration, validation, which is sort of like more the normal formal flow that you're used to. We also work quite a lot with FPGA implementation, and we've got some new projects up, new areas that we're working with. One is agile design evaluation, which is helps designers to use formal really early on in their projects, being able to test their design before it's completely written and before you've even written a line of test bench. Also, safety critical verification on where you can inject faults in your design and see that the safety critical circuitry is working correctly. And we can also read System C and C++ right now, so you can actually run formal on your System C and C designs, which is interesting to some people. If we've got a stand over there, you can come talk to us if you're interested, if you don't know any of this. So yeah, your feedback is very appreciated. If you've got a particular bee in your bonnet about any of these subjects, we'd love to hear from you. In summary, basically, it's a simulation. Formal is a powerful combination, and really you need both. Nowadays, designs are not getting simpler, but more complex, so the need for formal is only increasing. And we're working on several different connection flows to help with that, to make formal and simulation connected tighter. Like, for example, coverage data through UCIS and operational assertion and integrating different models. So was it? Am I well in time?
Well in time. Thank you very much.
Right. If you got any questions?
So
This one there.
sorry, can I just hand you the mic and ask you to introduce yourself as well?
My name is Sadat Rahman. I'm from Ericsson, Sweden. My question is, what do you mean by common coverage model that is applied both for formal and simulation?
It's that's a very good point and a deep point also. I mean, at the most basic level, it means that you can, in your verification planning tool, if you've decided that there is a particular part of the functionality that you want to have covered, and you covered it in formal, that there is an automated way of porting this coverage, this knowledge that this functionality is covered into your verification plan. But of course, there's more facets to this that we can't get into right now. It's on the type of particular coverage. Is it just executed? Is it observable? Like I've said there. So there is there's more technical trickery lurking behind there. But the first thing that you need to be able to do is actually make sure that the tools can talk to each other and they can share that kind of coverage information. People are using this right now, but the flows that they use are really not very standardized and formalized, but scripted type things.
And I also have a follow-up question. Do you think the vendors are actually going to merge the simulation coverage both from the functional and the code one with the formal ones in the near future? We've already talked about the common database that Axelar is working on. So can we expect that in near future we will be able to merge the coverage database from simulation and formal together?
That's the aim. I mean, I think the problem is more political or whatever, I don't know, strategic, not technical, right? I think all the big EDA companies are coming to the realization that the standardization of some sort is good for everyone. Like I've said, we're because we've got common customers. OneSpin's already collaborating. It's actually on different things, collaborating with all the big 3 EDA vendors on certain things, and certainly with Mentor and Synopsys on this stuff.
Okay. Yeah.
So
thank you.
Is that for UCIS? Is it? Okay. So there's the for those. Okay, thank you. For those who don't know, there's UCIS is the coverage standard, isn't it?
Well,
coverages.
Yeah, it's a proposed thing from. There's technical things still to be sorted out there.
Okay. There is one question online from Claudia Blank. I think it's based in Munich, and she asks, "What do you cover all of System C, basically? So do you cover the whole language of System C or not?"
At the RTL level. So if the System C as if it was, I mean, it gets interpreted by the tool as if it was Verilog or VHDL RTL, right? So it has to be written at that level. Maybe you got a little bit of freedom there, but it should be synthesizable, basically.
So if it can go for a HLS tool, it should be able to go for your tool, shouldn't it?
That is one of the biggest applications for it.
Okay.
Because I mean, you don't want to debug the output of the HLS tool if you want to do some formal verification with it. You want to use the source code, which is readable, right? So.
Okay. So as well as doing property checking on System C, can you do equivalence checking between System C and RTL?
Well, not with an equivalency checking tool yet.
Okay.
I mean, you can fake it up, I guess, with if you write good properties, you can verify the two together, but it's not our EC tool, equivalency checking tool, can't cope with System C yet.
And one more question. So you mentioned about designers, trying to put this in the hands of designers. You also mentioned about taking assertions and moving them to the UVM test bench. So do you foresee a situation where designers could write assertions to visualize their design, and then the verification engineers reuse those assertions and properties directly into their test bench?
Yeah, certainly. I mean, that would be one thing that can happen. We're very much interested in hearing feedback from the people in the trenches using this stuff to see, what would be most useful for them and what applications, are they're most interested in right now. But that's definitely one that could be.
So just we'll ask if there's any more questions from Bristol, from Reading. Sorry, I must be missing home. I think that's it. So I think we're just a couple of minutes ahead. So thank you for that. Thank you very much for the talk.